So we're looking at this Lambda service, which is one of the serverless compute services available to us. And what we can do so far is we can use the CDK framework um, to create a Lambda function resource, and we can also trigger the execution of that Lambda function using the CLI or using a web client if the Lambda has a URL generated for us, and we can control the generation of the URL from our CDK stack code. So that's kind of where we left off the last day. And if I pick up the story from here, so we were talking about the different Lambda integrations that are available to us. And you'll remember what this is about is what are the different ways we can trigger a Lambda, or put another way, what other services can trigger the execution of a Lambda. And it turns out that most of them can really. Now, then there is it depends on which service is triggering the Lambda as to what what we call the integration model is, how the integration actually works. And there are three models available to us: synchronous, asynchronous, and pole-based. And as I was saying the last day, it's not so much that you have a choice as to which integration model you choose. You don't have that choice. The integration model really depends on what service is trying to trigger the Lambda. The synchronous integration model is used when we're trying to trigger a Lambda from the CLI, or when we're using the URL that's associated with the Lambda. And it's also used by the API Gateway service, which is one that we will look at in a couple of weeks' time. So that's fine. The couple of points that we made, I just thought I'd bring up my pen here. We need to keep remembering that, it's not that you're talking to the Lambda function directly. The actual Lambda service is always sitting between the Lambda function and whoever the client is, whether the client is the CLI, API Gateway, or some sort of application running on your desktop. That's always the case. Sorry, I jumped. I shouldn't have. And the other main point was that in the synchronous model, synchronous integration model, the client, whether it be this or this, the client is responsible for dealing with any errors that might be thrown by the Lambda function. Typically, like what the client will want to do is maybe to retry the execution of the Lambda. But it's up to the client to handle all of that. For the asynchronous communication or the asynchronous integration model, things are a little bit different. So first of all, the services that use this model would be S3. So we can actually cause an S3 bucket to trigger the execution of a Lambda. SNS, which is a kind of messaging service, can be used to trigger it. CloudWatch alarms can also trigger a Lambda. And I'm saying here that if we look at an example, right, the image down here where S3 is actually the event source, as we call it. What you can do is you would see, explain or declare this in the CDK stack file. You can say that if there is a state change in a particular S3 bucket, then I want that to be the event that triggers the execution of a particular Lambda. Here's my Lambda over here, my Lambda function. And so the state change might happen as a result of either using the CLI or some application that's running outside of AWS causes a state change, maybe upload an image or upload a file, delete a file, change the contents of a file in the bucket. All of those would be state changes. That any one of those would cause the S3 service to tell the Lambda service about the state change. And then it's the Lambda service, what it will do is it will take the information that it has received from the S3 service in this case, it'll put that information into an internal data structure or a queue, and it's the Lambda service that would actually trigger the execution of our Lambda function, passing in essentially the contents of this structure here. And the Lambda function then, processes the actual events. S3 over here, it's not going to wait for any response back from the Lambda function. It may wait, it may acknowledge a response back from the Lambda service, all right, essentially saying, I got your message, I got your event, but it certainly isn't going to be waiting for the Lambda function. And so that's why it's described as asynchronous. There is no kind of request response sequence happening here at all. And certainly whatever was the original source of the event, that certainly won't get any kind of acknowledgement as to whether the Lambda function executed successfully or not. If for whatever reason the Lambda function does not execute successfully, like it throws an exception in the middle of its execution, or it times out before it can complete its execution, in either of those cases, it's the Lambda service will actually retry the execution of your Lambda function, and it retries 3 times. So in a way, it's the Lambda service that is handling any errors that might occur during the execution of the Lambda function. When we were talking about the synchronous integration model, we said it was the client, whether that be here or here, right? It was the client that was actually responsible for handling any errors that occur in the Lambda. It's not the client in this case, it's actually the Lambda service will do the retries. And it limits itself to 3 retry attempts. Okay. That's asynchronous. We might see this actual integration model further down the line. The third integration model is called event source mapping, kind of a peculiar name. Pole-based is slightly more descriptive. It's a little bit like the asynchronous, but there is one main difference between the two. Now, first of all, the services that use this integration type would be DynamoDB, SQS, which is a messaging service, and something called Kinesis, which is a kind of a streaming service. If we take DynamoDB, which is a database service, what we're illustrating over here is an example of that. And so this is a database, DynamoDB database. And let's suppose what we want is down here, we've got our Lambda function. We want this function to execute whenever there is a state change in DynamoDB, in a DynamoDB database. State change being new record has been added, record deleted, record updated, that kind of idea. So something some external application will, write to the database or cause a state change. In fact, this could actually be a Lambda, but it doesn't really matter. Something anyway causes a state change in DynamoDB. Now, what DynamoDB does not do is it does not tell the Lambda service about the state change. What actually happens is the Lambda service periodically polls the DynamoDB service, asking it, have there been any state changes in your database since I last polled you? It will respond with whatever state changes have occurred. This record was added, this record was deleted, these two records were updated, you know. Um, so it's a batch of changes. It gives the batch of changes back to the Lambda service. Again, the Lambda service actually stores those inside in some sort of internal structure, data structure, queue. And again, the Lambda service calls the Lambda function, passing it in the contents of this queue. Okay, but the main difference here is it's the Lambda service asks the other service, have there been essentially, are there any events that you need to tell me about that are of relevance to this Lambda function? In the case of the synchronous integration model, it was the other service that told the Lambda service about the state changes. So the kind of the flow is in the opposite direction. We may see this as well later on. So that's they are the three integration models. All I'm getting across here is look, the Lambda service, in fact, every service on AWS has an API, web API interface to it. That's how we actually interact with it, you know. And this is a RESTful API. There's also an SDK toolkit that's provided by AWS for us. And all of the other services that potentially communicate with Lambda use the SDK internally, like API Gateway, which we look at. We were talking about S3 there a while ago, talking to the Lambda service. Well, it actually uses the Lambda SDK to do that. Or if we were using the CLI, it's using the SDK. Okay, so that's what's happening. And if we write a Lambda function, and sometimes the Lambda function actually wants to talk to the Lambda service, well, it would use the SDK as well. Now, the next few slides are important, but I'm actually going to skip over them because I want to move on to another service, mainly so that we can make more progress in the labs. So I'm going to skip over these couple of slides, but I will definitely come back to them because they're telling us some important aspects of the Lambda service that we should be aware of really as developers. So we're parking Lambda for now, and we're going to talk about the service called DynamoDB. And it's a serverless NoSQL database service. And we know a lot about NoSQL databases, Mongo in particular. There are also serverless relational database services, but we won't look at them. We're going to just look at this one. So we need to familiarize ourselves a little bit with DynamoDB. First of all, it's a NoSQL database. That's fine. I'm saying here it's fully managed. Fully managed is a kind of byword for serverless. There are obviously DynamoDB servers running in the AWS cloud, but we never deal with them directly. But they're certainly there. But they're managed by AWS for us, so that's classic serverless. I'm also saying it's a highly available service. Now, what actually happens behind the scenes is when we create a DynamoDB database, the DynamoDB service will automatically create replicas of our database across 3 availability zones. Yeah, and that's why we say it's a highly available service. We're never going to get caught with that situation where a particular AZ zone is unavailable, and therefore our database is sitting inside in one of those AZ zones, so we can't access it. That obviously would be non-desirable. So the DynamoDB service will automatically handle replication database replication for us and synchronizing them and all of that kind of stuff and making sure that they are consistent. In other words, there's eventual consistency, which I'm sure you've heard about in your MongoDB studies. Serverless, sorry, not serverless, schemaless. That's an important quality. MongoDB has this as well. Schemaless essentially means that you can have records in the same table that have a different structure. All records in one table do not have to have the exact same structure or schema. So that's fine. Now, of course, because DynamoDB is non-relational, then you don't have table joins, you don't have referential integrity, you don't have foreign key fields. In fact, you don't have SQL. You've no corresponding query language as sophisticated anyway as SQL available to you. And that becomes slightly problematic maybe, and it certainly means you need to put some thought into the design of your DynamoDB databases, as we'll see later on. It's fully integrated with IAM, so all the security aspects that you might, security characteristics that you might want to have for a particular DynamoDB database, you can implement those using IAM policies, as we'll see. That's okay. DynamoDB basics. Now, there's a slight change in the terminology when we use DynamoDB as opposed to other kind of databases. Well, first of all, a DynamoDB is made up of tables. That's okay. That's a term we use a lot. Each table has a primary key. That's okay as well. That's a term that we use a lot in the relational world. The primary key must be unique. That's all fine. We don't talk about records as such. It's just a terminology issue, but we talk about items in a table. An item is essentially a record, right, or a row, but for whatever reason, they like us to use the term item instead of record. I'm saying each item has attributes. Now, in the relational world, we talk about columns in a record, but it's attributes in an item in this case. They're kind of the same thing, but it's just different terminology. This attributes idea, this is where the schemaless comes in. So we would say that in a particular table, the items in that table may have different attributes. That's what schemaless really means. However, the primary key attribute, that has to be the same for every item in a table. That would kind of make sense as well. So we have the notion of the primary key attribute or attributes, maybe more than one. And then we have the non-key attributes that make up a particular item. Maximum size of an item is 400 kilobytes. Okay, so there is an upper limit. DynamoDB has its own native data types, which I'm listing here. And they're kind of similar to, but at the same time, they're not identical to the data types that you might use natively within, let's say, TypeScript or JavaScript or Python. But they're close enough. But they are slightly different. Certainly these ones here might be slightly different. And the kind of conversion from DynamoDB's native types to the data types that you might be using within your code, there has to be a kind of a conversion from one to the other. Fortunately, we don't have to worry much about that, although we do have to declare that the conversion has to take place. I want to talk a little bit about the primary key part because it's obviously very important. There are two options I'm saying here in relation to the primary key. One is where the primary key is just made up of one attribute. We often say that it's a simple primary key. That particular attribute also has a second role, and that's why it has a second name, and it's called the partition key. So sometimes the primary key and the partition key are one and the same thing. I'll explain in a slide or two what this kind of relates to, but essentially what the partition key determines is where the item is stored in the database. It kind of controls that. The partition key, unfortunately, also has another name called a hash key. The partition key, it must be unique. It must be unique for each item. Kind of makes sense. Certainly it makes sense if the partition key and the primary key are one and the same thing. But certainly the partition key must be unique when it is the same as the primary key. And the partition key range of values should be diverse. Kind of makes sense as well. There should be kind of a wide distribution of the possible values of the partition key / primary key. Simple example, if you've got it's an obvious example. You've got a table of users, then the user ID is a sensible partition key, and it would also be the primary key when you've got this simple scenario. The second type of primary key is a composite primary key, and that arises when it's two attributes make up the primary key. One of the attributes has to play the role of the partition key yet again. The second attribute is often referred to as the sort key or range key. This combination of sort key and partition key must be unique for each item in the table. Okay, the partition key now will no longer be unique for each item, but this combination does have to be unique. The combination, that's okay. When you've got this composite primary key, what actually happens is you're going to have a number of items in a table that have the same partition key but a different sort key. And what you can be guaranteed is that that set of items will actually be kind of stored beside each other in the table. DynamoDB kind of takes care of that. They're grouped together in the table. And if you try to read all of the items that have the same partition key, like if you execute a read request and you say, I want all the items that have the partition key ABCD, then you're going to get the collection of items that have that partition key and they're going to be ordered by the sort key. Sorry, I should say as well like that we have this notion of an item collection in this scenario, and an item collection is simply a collection of items that have the same partition key and a different sort key. And that collection, when they are read from the database, they will actually be ordered by this in sort key order. Simple example, let's suppose in a gaming application where you've got users in games and you want a table that records information about every user's playing of a game. What's their maximum score in a particular game, that or whatever. When did they last play this game? That table, its primary key could be a composite primary key, and the partition key I'm suggesting here, the partition key could be the user ID, and the sort key could be the game ID. Yeah, for example. Here's another example with your kind of standard uh, uh, table that contains orders for goods, right? Now there's two ways I could design this table. So this table is going to have an item for each order from a customer. Yeah. Now I could first of all decide maybe I'm going to choose a simple primary key for this table, and the primary key is going to be the order ID. That's what I'm saying over here. And it's a simple primary key, and certainly, every order will have a different order ID. So that's a suitable primary key for this table. And in this case, the partition key is the order ID. Alternatively, I could come up with this idea. I'm going to use a composite primary key. And I've decided that in this case, though, customer ID is going to be the partition key, and order ID will be the sort key. Sorry, am I right? Yeah. Order ID is going to be the sort key. Customer ID is going to be the partition key. And in terms of item collections, that now means that all of the orders by a particular customer, they're going to be kind of grouped together. And it looks like these two have the same customer ID. So this would be an item collection. Yeah. Now the question you might have is, well, which one should we choose? Should we go with the composite primary key, or simple primary key? And the answer to that question is, it depends on the type of queries that your application needs to make against this table. If the application only ever wants to read items just based on the order ID, then use this design. However, if your application will want to read orders based on a customer ID, like give me all of the orders for customer 1234, for that type of query, you have to use this design. You cannot run that type of query against this design. If you did, then what you would actually have to do is you'd have to read the entire contents of the table into your application and just programmatically filter through all of the items, picking out the ones that have a particular customer ID. Because remember, DynamoDB does not support the SQL query language. We'll talk a little bit more about that now later on, but that's a preview of this whole kind of partition key, primary key, sort key aspect of DynamoDB. Just to go back to the whole partition key and what's the significance of that? What I said a while ago was that it controls where your data is stored in the database. This is the partition key now, right? So what actually happens behind the scenes is DynamoDB breaks up a table into partitions. Each of these partitions is going to sit on a particular node within the AWS network. A partition size, the maximum size is 10 gigabytes. I probably should have said on the very first slide about DynamoDB is DynamoDB is really designed for very large databases, like, hundreds of gigabyte type databases. That's where it really shines. Um, and so, it's highly scalable. So anyway, so a table is automatically broken up into partitions. This has got nothing to do with replication now. So it's broken up into partitions, and as your table grows, DynamoDB will start adding more and more partitions automatically behind the scenes. That's fine. So let's supposing this is a snapshot of a particular table now, not a database, just a single table. This table has 4 partitions. So given that a partition is 10 gigabytes, we're talking about, certainly over 30, well over 30 gigabytes of data so far. And let's supposing it's our orders table, yeah? Now, let's supposing we want to write a new item to the table, or in DynamoDB, we talk about a put item operation. And let's also suppose that our table is using the composite primary key that I was talking about. So customer ID is the partition key, and order ID is the sort key. And there will be other attributes as well. When we send this request to DynamoDB, what it does is it takes the partition key value, puts it through a hashing algorithm, and the output of this hashing algorithm will be the partition number that the item should be written to. So it'll either be 1, 2, 3, or 4 in this case. And DynamoDB then sends the actual item to the particular partition. Now, these partitions are running on separate server nodes, and those server nodes are running part of the DynamoDB service itself. So, this kind of router component within DynamoDB sends the item to the DynamoDB service that's running on this particular node, and it takes care then of writing the item into the partition. Similarly, if our application tries to do a get item, which is kind of a read operation, it specifies the exact primary key of the item that it's looking for. In the same way, what happens is this DynamoDB router component will take the partition key value, put it through the hashing algorithm. That will tell us which partition instance it should forward the GET request to. And let's say it's partition 2. And then the DynamoDB component that's running on this partition will get the actual item itself and return it back to the requester. So overall, the role of the partition key is to determine which partition an item is stored in. And that's why it's important that your partition key that you choose has a very diverse range of values, because obviously you'd like your data to be kind of distributed fairly evenly across the partitions. There's 2 benefits to this whole idea. One is scalability. Doesn't matter how much you want your table to grow, DynamoDB will just keep adding more partitions to it. The other main benefit is, I'm saying, consistent performance. Consistent performance in that, certainly for read operations, DynamoDB can guarantee that a read operation is never going to take more than a particular time to complete, and the way it can guarantee that is it knows that a partition is never going to be more than 10 gigabytes in size. I mean, the hash this hashing function, its performance is always going to be the same, and we can be a partition, a read operation from a partition. You know that there are certain guarantees that DynamoDB can make in terms of how quickly an item can be read from a partition because the partition size is limited to 10 gigabytes. Okay, so that's a little bit of background in terms of this partition key and its role. Okay, how do we actually program any of this stuff? What I'm showing you here is an excerpt from our CDK stack. And in the CDK stack, you actually talk about just tables. You know, you ask, or you express or declare that you want a particular table to be created for you. You don't really deal at the database level, it's at the table level. So table here is another example of an L2 construct, which we've talked about a lot. And like all other constructs, its arguments, it has three arguments. The first is the scope of the construct, as in this case, we want the table to be part of the current stack. This is just the construct ID, and the rest then is the configuration for this particular construct. And the configuration depends on the nature of the construct. So because of it's a database, the billing mode I wouldn't worry about. That we're always going to have the same billing mode. Here we're specifying what is the partition key attribute for this particular table. This is meant to be a table that contains movie details. Okay, so I'm saying the movie ID attribute is going to be the partition key, and it's a number attribute. The retention policy, the removal policy, what that controls is when, if ever, should the table actually be deleted by CloudFormation, like when we do a CDK destroy, what do we want to happen to our table? And I'm saying here, well, when we destroy the stack, we want the table to be destroyed as well. That's fine in development mode, but certainly in production mode, you more than likely would not use this removal policy. You'd like to hold on to the table um, uh, even though you're destroying the actual stack, because you're going to lose all the data in it. And that's fine. And down here, I'm just showing you. So I've got a stack deployed that has a table like this. And if I just jump into the management console and go over to DynamoDB, and select tables. Now I've got another table as well, but these tables are just completely independent of each other. You know, there's no sense of, well, this table belongs to one stack and this table belongs to another stack, or they both belong to the same stack. DynamoDB doesn't know anything about stacks. CloudFormation does, obviously, but so if I just look at the movies table, or the movies resource, I suppose, DynamoDB resource, and I can actually look to see, I can kind of poke around and look, it has these items in it. So I have seeded the table already. So if all my if all that was in my stack was this piece of CDK code, then it would create the table. It doesn't seed it, obviously. I need to do something extra to seed it. Now, ultimately, we will want to manipulate our database, and in our case, manipulate it from a Lambda function. So what I'm saying here is that, well, DynamoDB, just like every other service, it has a web API interface and it has an SDK that facilitates communicating with the API. And this SDK is what we would be using in our Lambda function. Um, all I'm saying up here is that uh, there are there are three clients, kind of DynamoDB clients that you can use to communicate with the DynamoDB service. The one that we will mainly use is this one here, DynamoDB document client. But internally, that uses a client called a DynamoDB client. All right. This is kind of more low level than this one. This is a higher, this one here is kind of higher level of abstraction and easier to program with. The middle one, we won't be using at all. Uh, let's jump over to VS Code. So if we look at the stack, now there is some stuff in this stack that we can kind of ignore for now, but so here's our movies table that we saw on the slides. I happen to have a second table that I can ignore for now. Uh, I have some seeding data as well down here. Okay, so I've got an array of movie objects, I suppose, yeah. And I want that to be my seeding data. Now, the way we actually do seeding, it's kind of clumsy enough, but the way, if you think about it, when we deploy this stack, we can't do the seeding until the table has been created and the DynamoDB service is happy that the table is now fully configured. So there's a timing issue in terms of the seeding of the database. We don't want to do the seeding ourselves separately. Ideally, anyway, we don't want to do it separately after we've done a CDK deploy. We would like it to be part of the CDK deploy, but clearly the seeding cannot execute until the DynamoDB service gives the OK for it. Yeah. So it's kind of an edge case. And there are some other edge cases as well when you're deploying stacks. And the CDK framework has a construct that's specially for these kind of edge cases, and it's called, AWS custom resource. So it's an odd kind of thing. It's quite difficult to configure. So if you don't mind me saying, I would say, look, just take all of this as boilerplate code for seeding our database. I explain it a little bit in the lab because this is what you'll be doing in the lab. But for now, look, we'll just say, look, this AWS custom resource, we are using it to seed our database for us. Yeah. And we'll kind of just park it at that. I've got a Lambda function here, and this Lambda function is going to be reading from my movies table. Now it has all of the configuration that we've seen before. What's new is this part here. You can pass in environment variables into your Lambda function, and they can be anything you want them to be. In this case, I'm actually passing in the name of my movies table, and I'm also passing in the region. It's hard-coded, which isn't great, but for now it's okay. I'm passing in the region. Essentially, it's the region that my table will be deployed in, the AWS region that it's deployed in. And other than that, okay, there's some other lambdas, but I'm going to skip over all of those. Well, sorry, I'm generating a URL for my Lambda, so I can trigger it from a browser or Postman. The Lambda itself then is this one here. And this is the beginning of the Lambda function, but this line of code here, this is a classic example now of initialization code for a Lambda. and kind of running out of time now, which I knew would happen. But what I'm actually doing here is I'm just calling a local function. So if I scoot down to the function, you can see that the first thing it does is it creates a DynamoDB client, which I mentioned on the slides. So that's the kind of the low level native, well, not native, but it's a low level client for talking to the DynamoDB service. We don't like using that one. We prefer to use the DynamoDB document client. But anyway, we need to create an instance of that, which we are. Then this stuff here is about how we convert data from essentially TypeScript to DynamoDB's native types in both directions, whether we're writing to the database or reading from the database. And we talk about marshalling and unmarshalling the data. Marshalling the data is when we do a write operation. Unmarshalling is when we do a read operation. And again, what I've highlighted here, you can again kind of take as boilerplate code. Essentially, what we're kind of describing here is how do we want, for example, if we are, which one is it? Oh yeah, if a property in a JavaScript object is empty, like an empty string, how do we want that to be? Do we want that property to be included in what's written into the database? And it looks like we're saying, yeah, we do. So we want the empty string to appear in the database attribute. This one is if there's a property in a JavaScript object that its value is undefined, do we want that included in the attribute that appears in the table? And it looks like, yeah, we do. So, they're kind of edge cases, and there's a similar kind of configuration for when we're reading from the database. So, like I said, kind of treat this as boilerplate as well, but we do have to specify some marshalling and unmarshalling rules. And the last thing we do in the function is we create an instance of our document DynamoDB client. Yeah, and that's what we're returning. And we're returning it back to here. So this now is going to be a reference to a DynamoDB document client. In the body of our Lambda function then, this Lambda now is going to, it's going to be passed a movie ID as a query string through the URL. Yeah. So that's what I'm doing here. I'm actually, the query string is actually going to be available in the event object, and I can show you that maybe later, some other time. So the net effect of this code here is I now have a movie ID available to me. I'm just doing some checking here. If there is no movie ID, then I should return some sort of error back to the client, Postman in this case. Otherwise, I can actually send the request to DynamoDB. So I'm using the document client. Now, the document client, the way it's designed, it only has one method called send, and the argument to that method is what we refer to as a command object. You can see here I'm creating a new object, and in this case it's an object of type getCommand. So these command objects, they're all contained within the command classes. They're all contained within the DynamoDB SDK. So the get command, as you might expect, that will kind of translate into a read request to DynamoDB. And in my get command, I am specifying what table do I want the request, the read operation performed on, and I'm extracting my environment variable that I've passed in. And I'm also specifying the primary key value, which in our case is the movie ID, because it's a simple primary key scenario, so it only has one part to it. So that's a simple illustration of how we read from DynamoDB. We use a DynamoDB document client. We pass a command, a particular type of command. That could be a get command, a put command, a delete command, a query command. They're all the different types of commands. And we'll see most of them later on. And of course, we are communicating across the network between this Lambda and the DynamoDB service. So this is an asynchronous communication, HTTP asynchronous communication. What is returned back is a data structure, and there's a particular property within that data structure called the item property, and hopefully that property will contain the actual item or record from the table. But I am checking to make sure that there is an item property. Otherwise, it would mean that we passed in an invalid movie ID essentially, and I'm returning an error message accordingly. If that's not the case, then here I'm just constructing the body of the response that I want to send back to the client. And again, I'm including the actual item itself, and that's what I return back. Yeah. And just before I wrap up, if I test, so I've deployed the stack already, and I have the URL of that Lambda that we've just been looking at. And so if I go to Postman, I have a Postman collection here, and I've got a variable called getMovie. I've set it to the URL of the Lambda function, and to set up a GET request, I'm sending a GET request to that URL. And here I'm adding on my query string, movie ID equals 1234. And I can tell you that there is a movie with that ID in the database. And if I trigger the send, I don't get the right answer. Sorry, it should be 1234. And here's the movie here, returned from DynamoDB. And we can, we could confirm it either way. We could go into the DynamoDB service. And you can see it there. Yeah, there's movie 1234. And it was also, if we looked at the seeding data, here's our movie 1234. So it all seems to line up correctly for me. Okay, as usual, I've kind of run out of time, but what, let's see, if we go to the lab, everybody now should complete up to the exercise, up to and including the exercise. This part here, as I always say, you can work your way through it if you wish, but we have not covered this part of DynamoDB, which is what are called local secondary indices. And I would like to try and cover those on Thursday. So I definitely want people to be able to complete this lab and know what they're doing by the end of this week. The first assignment, which, okay, it's another couple of weeks away, but first assignment will involve Lambdas talking to DynamoDB, plus some other services as well. Right, that's it for today. I will touch base with you again on Thursday. Thanks, bye-bye.